Okay, here we are finally. All right, well, welcome to another episode of Science and Technology Q&A for kids and others. We had a bunch of questions saved up from last week, and maybe we could start with some of those. There's a question from Will here. Is there a physical principle that governs Moore's law? Why is there so much available computation? Okay, let me talk a little bit about that. So what is Moore's law? Moore's law is an empirical fact that was originally suggested by Gordon Moore, who was then CEO of Intel, largest manufacturer of microprocessors in the world. And his rule of thumb was, I think it's processor speed doubles every 18 months. I think that was the claim. And that was something that was said back in the 70s, 80s. Computers were getting faster. Computers were getting faster every, doubling in speed with some considerable rate. And it was sort of an impressive thing. And for a long period of time, and I remember people saying, oh my gosh, one day we'll have gigahertz speed microprocessors. What does the speed mean? The speed means every instruction that gets done by the computer, every machine code instruction that gets done by the computer, how long does it take? Well, actually, more accurately, there's usually a clock that is one tick of the clock. An instruction may take one click of the clock, 2, 3, 4 different instructions take different amounts of time. Typically, reading one piece of data from memory takes, depends where it is. There are different levels of memory, but the fastest will take maybe one clock cycle. But anyway, so the question is, how fast is the clock? And if you look up on your computer, I could look at my computer here. I'm sure, let's see, what is it? This is a 2.7 gigahertz computer. So that means that nearly 3 billion times a second, there is a clock pulse where something can happen in the computer. So I remember back in the 1990s, people wondering, when are we going to make it to a gigahertz? Are we ever going to make it to a gigahertz? It was things like there were, 1, 2 megahertz CPUs, things like that. How can we go faster? How can we go faster? And the impressive thing was that every couple of years, it was like we're pretty much doubling the speed of processors. And how was that achieved and what's happened? Well, the bad news is the last probably 10 years, there really hasn't been that much increase in speed and core speed of processors. Those clock speeds have stayed pretty much the same. Maybe they've climbed from 2 gigahertz to 2.5 gigahertz to, maybe you see some things at 3 gigahertz, those kinds of things, but it hasn't climbed that much. Now, that's sort of the bad news. The good news is that a lot of actual applications that people run have gotten somewhat faster. And the main reason is that they're not just running on a single CPU at a time. It's not like you have a program that's just sequentially doing this. Instead, you might have 1,000 parallel threads that are running where different pieces of the program are all running in parallel. So for example, let's say you are putting an image on the screen and you've got to decode some pieces of the image that are coming in from some stream of data. You might be able to do that by, in parallel, dealing with one part of the image at the same time that you're dealing with other parts of the image. So as far as you, the user, are concerned, you've got a computer that's 1,000 times faster because you've got 1,000 parallel threads operating. Now, in typical computers, the typical, like a laptop, you might have 4 core CPUs. So your CPU might be able to do 4 parallel threads of computation at the same time, of ordinary kinds of computation, but there also are GPUs, graphics processing units, that are able to do often 1,000 or more parallel computations, but they're not general computations. They're specifically computations where you have arrays of numbers and you're able to do the same thing to every element of that array of numbers. Originally, GPUs were developed for, as their name suggests, rendering graphics and things. Then they were really driven a lot by computer gaming and wanting to have as high quality and as fast as possible graphics for computer games. But in more recent times, GPUs have been used for all kinds of purposes. Your average just typical program that's written in a general purpose way won't run on a GPU. It has to be specially coded to be able to run on a GPU, but that's the main thing that's achieved an increase in speed as a practical matter for people running programs. Now, in terms of the speed of actual CPU chips, it was very mysterious that that there was this sort of inexorable exponential law that operated, because really what was happening sort of on the ground was lots and lots of engineering details. So what limits the speed of a CPU chip? Roughly, so a CPU chip has on it these tiny little features etched into silicon that represent little tiny wires and places where the wires cross to make transistors and switches and so on. And there might be a billion of those on a modern CPU chip. And they're made by taking essentially this giant sort of photographic image of this giant street map that is the network of wires and crossings between wires, and then essentially just almost optically compressing it down, actually done with ultraviolet light because you need to do that by now, and sort of projecting it down onto this tiny little chip. And then what happens is where the light falls, you can etch away a level layer of the chip with acid, and then what you get left over is this whole region of your sort of your pattern of wires, so to speak. So that's but now one of the things that limits the speed. So a few things limit the speed of the chip. One is there's a certain rate at which you can kind of fill up with electrons and get rid of electrons when you go through all of these wires and switches and so on, the capacitance of the system. And these days, I think it's probably about 10,000 electrons per bit, at least in memory. In CPUs, it's probably a little bit more than that, of how many electrons represent every bit of information that's going through the system. And the other issue is that there are many other issues, but another issue is that it's you can reduce this capacitance. You can reduce this sort of how much stuff you have to schlep around by reducing the sizes of the features, by getting down to, I don't know, a few nanometers, few billionths of a meter of size of these individual wires and individual switching areas and so on. So one issue is can you make that smaller, smaller, smaller? And then there are issues like, well, if you have two wires that are really close to each other, maybe the electrical signal from one wire, there'll be crosstalk with the wire next to it. How do you make rules for designing the sort of layout of wires and switches so that you'll minimize the amount of crosstalk but still achieve the objective that the circuit has? So those are a few of the kinds of issues, but it's a very, it's sort of the really pinnacle of precision engineering to be able to make anything where you put a billion, sort of features on this chip with a few nanometer separation between things. That's a huge achievement to be able to do that, and it requires a lot of pieces of precision and avoid, any little piece of dust that gets in there. That's a big disaster. You have to avoid all those kinds of things. It's just a progressive thing, and as one tries to build up a sort of production line for making things, there's always, oh well, there was this little thing that goes wrong 10% of the time. Oh, let's fix that. Oh, now there's another thing that goes wrong 3% of the time. Let's fix that. Oh, now that we've managed to get things to go to work better, now there's another issue that comes up, and you're progressively improving these things, and that's why you get this sort of progressive reduction in feature size and so on. And often when you get to a different level of feature size, you might have to change the overall technology you use. So for example, with visible light, if you're doing this etching process and you're using visible light, there's a minimum scale that you can deal with which is determined by the wavelength of light. And if you want to go below that scale, you have to deal with ultraviolet light or X-rays as a way to basically do that etching on a smaller scale. And what tends to happen is that as you bring up kind of a new technology, a new process for producing, let's say, microprocessors, there'll be one of the issues is the yield will go down. So typically the way microprocessors are made, there'll be a big wafer of very pure silicon, and then you'll be etching all of these different little sort of circuit patterns onto maybe 1,000 different little regions on top of this wafer. And then and each one of those could turn into a CPU chip, let's say. But the question is, which of them actually work and at what speed? And so what tends to happen in the manufacture of these things is you'll produce this whole sort of a collection of candidate microprocessors, and then you have a testing device that tests all of them, and then some fraction of them will work, and some fraction, something went wrong. Maybe it was a little defect in the perfect arrangement of atoms in the silicon crystal. Maybe shocker, a piece of dust. I think that's probably a rare case now. Maybe it's some other kind of thing that went wrong, and so one of these candidate microprocessors won't work. But the issue is, if the yield is sufficiently low, if only 1% of the microprocessors you think you're building actually work, that's bad, and it's very expensive to operate everything just to get 1% yield. And then what can also happen, a pretty common thing to be done, is that you'll test these microprocessors at different speeds, and some of them will be like, that's good, that works at 3 gigahertz. Oh, that one, it doesn't work above 2 gigahertz, so we'll sell that as a lower speed CPU. This whole problem of yields is a problem that affects a lot of kinds of precision manufacturing of this type. I mean, I remember back, probably, when was it? Probably when large displays, large flat screen displays started getting made, there was a strange thing which happened for probably a decade, where people did have very large flat screen displays, but the yields were really low. So they were very, very expensive. And the problem with the display is, if something goes wrong with one pixel on the display and it's dead, you get to see that. You're looking at your display, it's like, oh my gosh, there's this dot somewhere on the display, it's just sitting there. So you really can't use that as a meaningful display. If it's something like a memory chip, you might have ways to just say, well, let's just not write data into that spot where things don't work properly. But let's see, the question is, so what's kind of happened in the last probably 10 years is that the Moore's law of exponential increase of speed for computers has flattened off as far as the actual raw hardware of the computers is concerned. I mean, I know, we have a lot of servers that we use for Wolfram Alpha, for example, and it's every so often it's like, do we need to buy new servers? Not really. They'd only be 10, 20% faster. It doesn't really make much difference. Not worth the money. And back in earlier decades, it's like, yeah, they just got twice as fast. They just got 5 times as fast. It's kind of a shame if you're developing software, because some assumptions that I've made, for example, about the complexity of software systems, it's kind of like I'd always assumed computers will always get faster. So it's okay, so long as the complexity of the software system doesn't increase, things will get faster as far as users are concerned. By the way, another thing that tends to happen is, as time goes on, software gets more and more complex, and there are more and more layers that get used. And so that can make things appear to go slower, even when the computer is running at the same speed. But today, I don't know how many CPUs there are in the world today. I'm guessing on the order of 100 billion. Depends exactly what you count, whether you count only general purpose computers that are running sort of general operating systems, or whether you count microcontrollers that are just, because a typical car might have a few hundred microcontrollers in it. Those are just sort of simple CPUs that do really just one thing and don't run a full operating system and so on. But there are probably 100 billion, maybe 1 trillion CPUs of some kind in the world today. It's a large amount of sort of organized computation. Now, what will happen in the future? One of the questions is one going to be able to make existing computers much faster? Does one have to use completely different technology? I mean, the whole sort of effort of making quantum computers, I'm not sure that the official use of quantum mechanics to make a magically faster computer, I don't think that's going to pan out. But the idea that there are different technologies for making computers, that's a good potential idea. My own belief based on science is that to get computation to happen is not difficult. What's difficult is to get the computation you want to have happen. I mean, let's say you've got a bunch of molecules in the gas in this room. They're swirling around all kinds of patterns. That's effectively doing a lot of sophisticated computation. The question is, can I feed in the input? Can I feed in the program I want and have that executed by molecules, so to speak, or not? And that's one of the interesting challenges, is can one make a, for example, molecular scale computer As I mentioned, the computers we have today, maybe it's 10,000 electrons per bit, 100,000 electrons per bit, these kinds of things. Could we get it down to the point where it's 1 electron per bit, where it's where things are operating at the scale of individual atoms, individual molecules, and so on? The one example that we have of that is in biology. In our sort of biological processes are operating at the level of individual molecules, are doing things in our bodies and are interacting with each other. And that's an example of sort of molecular scale computation, but we haven't yet managed to build sort of computer-like technology that operates in that kind of way, although I'm quite certain it's possible. It's something I've long been interested in, but I don't think we're quite there yet in terms of the sort of ambient technology to understand how to do it. Okay, let's see, tons more questions here. Let's see, there's a question from Joshua. If F equals ma and photons have a mass of 0, how can light sails work? Okay, interesting question. All right, so let's unpack that question a little bit. So first of all, what is a light sail? So there have been a few experiments actually done on these. You get the point is that when you have light coming from something, whether it's a flashlight or whether it's the sun, there is a small force that is exerted by that light when it bounces off essentially a mirror. Now, in practice, you get this big thing in space where you have a giant piece of reflective mylar or something that's I don't know, maybe a kilometer across. If you and potentially you have that so that you're using it as a solar sail, for example, where the light from the sun is hitting this giant sheet of mylar that has to be very thin and light, otherwise it doesn't. Otherwise, you're wasting all your effort on moving your sail, which is probably not what you want to actually move a spacecraft or something. So what's happening is light from the sun, for example, is hitting this essentially reflective thing, and it's bouncing back. Okay, so the question is, how does that work? Well, the answer is that what's happening when you have a mirror, a photon is going in one direction, and a photon has momentum. And when it bounces, just like if it was a billiard ball, when it bounces, it's transferring. The momentum is reversed. If it bounces, if it hits straight on, it bounces straight back. The momentum is reversed. But just like if you were to hit something with a billiard ball or just hit something at all, the momentum, changing that momentum and having it bounce exerts a force on the thing that's doing the changing of momentum. In that case, the mirror or the solar sail in this case. So the question is, why do photons have momentum? And there's in ordinary kind of everyday classical physics, there's a formula that Isaac Newton originally talked about back in the 1680s. Force equals mass times acceleration. So it says the amount of, so you can turn that equation around and say acceleration equals force divided by mass. So you want to make something go faster, you exert a force. The amount that it will go faster depends on how much force you exert relative to the mass of the object. So if you have a very massive object, you have to exert more of a force to get the thing to accelerate more. If you have a very light object, you don't have to exert very much force to get it to accelerate. Okay, so the question is, in that formula, if F equals ma, for example, how come if photons have a mass of 0, that's m equals 0, how come that all works? Well, the reason it works is because that formula doesn't apply to photons. That formula applies only to objects that are moving at speed slow compared to the speed of light. The full formula has it's m divided by square root of 1 minus v squared over c squared. It has an extra piece. And that extra piece is a consequence of relativity, special relativity. And that extra piece kind of tells you that actually that formula doesn't really apply at all to photons. And instead, you pretty much independently, you have to separately say a photon has an energy and has a momentum, and photons have momentum even though they have 0 mass. Obviously, that's an interesting fact about the world. And as we make our fundamental theory of physics, we have some understanding perhaps of how that really works, how you get momentum even when you don't have mass. Actually, it's not too hard to see how that works. It's a little bit elaborate to explain here, but there's it's not as difficult as one might think to have momentum without mass. In effect, so the full formula, people know, the famous formula, E equals mc squared. So that's a formula that says that the mass of an object, if you were to convert it all to energy, annihilate a particle and antiparticle, something like that, convert everything to energy, it's the mass of the particle times the speed of light squared is equal to the energy released. The full formula is E squared equals E squared equals P squared C squared plus M squared C to the fourth. So the energy squared is equal to momentum squared times C squared plus M squared times C to the fourth. That's the full formula that includes momentum. And that formula is much easier to sort of untangle in terms of how it works with photons and zero mass objects and so on. Let's see. Okay, there's a question from Ringmaster here. As of right now, what do I anticipate the outcome of the Wolfram Physics Project will be? What practical applications will it have? So our project is an attempt to sort of understand the lowest level machine code for the operation of the universe. And what's amazing is that it's going incredibly well. And I think we really are pretty certain that we know correctly what the overall framework for understanding what happens at sort of the lowest level of our universe is, and how space is made from a discrete collection of points where we just know the sort of the way that they're connected to each other in a giant hypergraph, and how time works by sort of computational processes going on, and how quantum mechanics works by this sort of whole network of different possible histories and so on. All of this stuff seems to be coming together, and all of this stuff we seem to be able to understand the things that were discovered in 20th century physics, particularly relativity and quantum mechanics. We now, what in the past people just said, these are facts that are true about the world. We can now say this is why they're true. This is how we build up to understand why relativity works the way it does, why quantum mechanics works the way it does, and that's very exciting. And, to this point, we are primarily making sort of theoretical predictions where we say, according to our very low level model, this is how things should work. And that's sort of fitting together. And we're seeing how it fits together with other kind of mathematical physics theories people have had. And a lot of times the sort of mathematical formalism can be applied, all those kinds of good things. Okay, so what? Well, according to our theory, space is not something continuous, it's actually discrete. But it's discrete on extremely small scale, maybe 10 to the minus 100 meters type scale. That's, let's see, that's a trillion, how many trillions? About that many trillionths of the size of a proton, which itself is a 1,000 trillionth of a meter across. So we're talking very, very, very small distances. Space is discrete. Why is that important? Well, if you had a black hole in your backyard, there are some effects that would take place around the black hole where that can matter somewhat. If there are mergers of giant black holes, some things about that can matter. But most of the time, it doesn't really have much significance at all. It's like saying, does it really matter that water is made of discrete molecules? Most of the time when we drink water, when we slush things around, when we have boats and so on, it doesn't make much difference to a boat that water is made of discrete molecules rather than being continuous fluid. And it's the same thing with the structure of space and so on for us. Now, I think that there are questions about, does the theory have implications that one can observe with telescopes looking at the large scale structure of the universe, or with particle accelerators looking at the small scale structure? The expectation is that yes, there will be a bunch of those things, and they'll be pretty interesting and pretty funky effects and surprising things about, fluctuations in dimension of the universe away from exactly 3 and all kinds of things like this. But they're not things that are likely to have kind of an everyday, oh yes, I see that every day type consequence, with a few exceptions. So I think the likelihood of getting to a sort of invention that one can actually use as a practical matter is a long-term story. I mean, I think it's like when Newton was inventing things like we talked about F equals ma, when he was inventing those kinds of things and his law of gravity and so on, at that time, he will have already known that it's possible to have satellites orbiting the Earth, artificial satellites. But 1687, Newton publishes his big book about applying mathematics to physics. He could have started a satellite launch company, but it would have been very, very, very much too early because the ambient technology wasn't there. And I kind of feel the same way about a lot of the things with our physics project. There are things where we can sort of imagine that it might be possible eventually, but there's a long chain of engineering to get there. So one of those I wrote about recently is, can you go faster than the speed of light? We've been sort of trained by discoveries in relativity from 100 years ago that no, nothing can go faster than light. Well, it turns out that going faster than light is a bit of a more complicated story because it depends. When you say I'm going to go faster than light, the question is, what is space like? Is space very much uniform thing where I'm going faster than light, or is space kind of a complicated thing itself, where the question of whether you go faster than light depends on whether you can sort of navigate through all of these complexities of space. And it turns out, I'm pretty sure that in our models, that in principle, it's possible to go faster than light. But to do that, you have to kind of solve a very, very difficult engineering problem. You have to be able to essentially hack space. You have to be able to decide. It's like if you're in, gas molecules in a room and you ask how long it's going to take for a gas molecule to go from here to the other side of the room. Well, most of the time, it takes a really long time because these gas molecules, they hit another gas molecule, it hits another gas molecule. They're kind of randomly walking based on hitting one gas molecule and then another. But occasionally, there'll be a gas molecule that has it exactly right, where it exactly knows, this is going to hit this one, then this one, then this one, and it's going to be able to go straight across the room. So it's the same kind of thing. If we can sort of hack space to the point where we can kind of predict all of the details of all the sort of microscopic randomness that happens down at this 10 to the minus 100 meter scale, if we could really hack that and navigate our way through it, then we could go faster than light, or at least we could send a signal faster than light. By the way, in the history of telecommunications, people have often had this issue of, how fast can you really send a signal on a copper wire? How fast can you really send a signal by radio? And a lot of times people said, oh, there's a limit because of this, because of that. And then people realize, oh, well, if you kind of hack the substrate, if you just figure out exactly when do you send it, how do you correct for this piece of noise that happens, et cetera, et cetera, et cetera, you can go faster. But we're not even close to, use this model to understand how to go faster than light. We can't even manipulate things at the level of individual atoms, molecules, let alone something that's trillions and trillions and trillions of times smaller than an atom or molecule. But I think, from the point of view of the significance of our project for the world at large, I kind of think a lot of the significance is more philosophical than practical at this point. And it's kind of reminiscent of what happened in the history of science a long time ago, like 500 years ago. If you asked a typical person, how does the Earth move? They would say, the Earth is staying still. The Earth doesn't move at all. The sun moves around the Earth. We can see it every day. The sun moves around the Earth. And we can see it every year that the sun is moving. So sort of the general belief was, well, we can tell, we're just standing right here. The Earth doesn't move, we can tell that. And then Copernicus came along and said, well, actually, the mathematics works out a lot better. We have a much better theory if the Earth goes around the sun. Now, in his particular theory, the mathematical thing he was trying to work out didn't make much of a difference because of the way sort of relative motion works. Earth goes around the sun goes around the Earth, kind of same difference. But there were details of the mathematics of how that worked with respect to other planets that worked out a little bit more elegantly in the way that Copernicus did it. The previous way of doing it using Ptolemaic epicycles had been really quite successful. And when it came to just calculating where's Mars going to be, where's Jupiter going to be, whatever, that method of calculating worked just fine. It was a little bit bizarre and ornate, and people couldn't understand why these weird crystal spheres would move in the way that they move, but you could calculate what would happen, you'd get the right answer. In fact, even today, when we do calculations, we are using mathematics that is essentially those epicycles again. Same calculational method, but the interpretation is different. Well, so Copernicus came along and said, well, actually, no, it works better, and really it seems like we should, in fact, the Earth goes around the sun. a revolution, so to speak, in it's the origin of that word. The thing that Copernicus, I think, and it's kind of a comment on the history of science. I mean, he waited to publish those ideas until he was dying, basically, because he was kind of like, I don't want all the blowback from people saying, oh no, that can't be true, et cetera, et cetera, et cetera. Instead, people like Galileo, who was much more of a kind of activist of his time, were the ones who kind of carried that forward and pushed it hard. But in any case, what was the main consequence of the Copernicus moment? The main consequence, I think, was that people got the idea that science can tell you things that aren't obvious to you. Like, I think I'm just standing still on the earth is standing still. How can you be telling me from science that's not true? The earth is actually moving. But it's so it's kind of a moment when sort of people got the idea that science can tell you things that are not obvious, and you can end up concluding things from science even though they weren't obvious to you. And arguably that whole process over the course of 500 years might have been taken a little bit further than it should have been, and people are now like, science is going to answer everything. We can answer everything with science. Actually, one of the things that has become clear from scientific work that I've done is that there are limitations. If you want to say to science, you have some system and it has some rules by which it operates, and you say, what's going to happen according to those rules in the system? Well, it turns out there's a phenomenon I call computational irreducibility that basically says you can't know what's going to happen except by just running the rule and seeing what happens. So that's kind of a limitation to what you might have thought of. Okay, science, just tell me what's going to happen. That can't work. There's this computational irreducibility that says you have to kind of follow through the steps, and it takes a lot of effort to find out what happens. In a sense, that's not a terrible thing for us to find out, because it's kind of like if you could always take any system in the world and say what's going to happen in the end, then it's kind of like a bit of a downer in terms of leading one's life, because it's like, well, what's going to happen in the end? The answer is going to be 42. That's the end. We can immediately know that. Well, no, we can't, because of computational irreducibility. The actual process of kind of the motion, the progression through time and so on, it actually, something real is happening. Some computation that isn't reducible is happening. Okay, so in any case, but sort of the Copernicus moment was this kind of trust science more than you trust your senses for some purposes. I think one of the things that happens by understanding sort of what is the universe really made of, how does it really work, what we're discovering is it's computation all the way down. There's really this idea of computation, these ideas that come out of sort of the computational paradigm for thinking about things, they really apply to our universe. Our universe really works that way. And it's not like, well, this computation is interesting for making computers, but it's not really relevant elsewhere, because really the world, the mind works differently, this works differently, that works differently. No, it's really computation all the way down. And that means that these ideas like computational irreducibility, which are a phenomenon of computation, they're ideas that actually matter everywhere, because really our universe is really computation all the way down. And it's just like back in the days of Copernicus, Galileo, Newton, and so on, people got ideas like force and momentum and so on. They got ideas about how the world works and these sort of paradigms of thinking about things, acceleration, et cetera, et cetera, et cetera. These were things that came out of that thinking about mechanics. And now we use them as metaphors to think about a lot of kinds of things in the world. We talk about, some idea having momentum or something. Actually, in that case, it's just a metaphor. It's not like we think it actually is moving with a mass and velocity and so on. It's just a metaphor that we understand because we understand kind of the logical structure of the way that mechanics works. Well, I think what we're seeing now is that we need to understand ideas like computational irreducibility, and we need, the reason that if nothing else told us we need to understand them is because that's fundamentally how our universe works. It's really computation all the way down. And that means that one of the things that we have to think about is in this case, rather than the mechanics case, where it's just a metaphor, we don't actually think an idea has momentum. We really do think that computational irreducibility applies to lots of kinds of things in the world, not just, for example, physics. So that's a little bit of a comment there. Oh my, there's so many things here. All right. Okay, from Mikhail. What is more difficult for you, to create things or to explain how they work to others? You know, for me, those two things have increasingly merged in my life. So, you know, sometimes when you do research, it's like, okay, figure out what's true. And then after you've finished, go explain it to people. And so a very typical thing is a lot of what I do is based on computer experiments. And a lot of what one does in computer experiments is making pictures, making of things. And sometimes back a long time ago, I used to make the following mistake. I used to say, okay, I'll figure out things at research level. I'll have kind of hacky, nasty pictures. And then when I've finished, I'll go and I'll make really nice pictures so that I can explain things to people. Okay. So I do that. And then, you know, I do all the things, I come to various conclusions, then I make the nice pictures. Then I look at the nice pictures and I'd say, oh my gosh, now that I have these nice pictures, I can see all this other stuff that I didn't notice before. So I realized that was a bad approach, and that instead the making the nice pictures that would be suitable to show to other people is something that's worth doing early in the process of doing the research, not as an afterthought. Because honestly, showing it, being able to show it to other people is as much being able for me to understand it myself. So I think it's been for me, it's you know, I you know, things like these events that I've been doing, trying to answer questions here. This is very educational for me. Whatever educational value it may have for other people, it's certainly educational for me. Trying to actually in real time answer a range of questions and understand how to explain things. But increasingly for me, I never really believe anything that I figured out until I can get it to the point where I've ground it down to something that's simple enough that I can explain it to other people or explain it to myself, or sometimes that I can write it down as a way, in a way that I would imagine I could explain it to somebody else. And increasingly, the things that I write, I'm fast enough and fluent enough writer that increasingly the things I write, I'll just write them once and then I'll show them to other people as well. Back when I was younger, I would write them and I would never show them to anybody else. I would use them only for myself. But that sort of changed over time. Okay, question from George here. Has the physics project shed any light on protein folding? Not really yet. I mean, let me explain that problem. So we are made of proteins. That's the most common kind of molecule in us, other than things like water and so on. Proteins are these collections of blocks of atoms that form amino acids, and our proteins might have anything from a few amino acids to millions of amino acids, all in a chain. And the question is, you've got all this chain of amino acids, and the question is, and there are about 20 kinds of amino acids that exist in us, and the question is, when you have this big long molecule that's in this long chain, what does it actually do? Does it stay in a long chain? Does it fold itself up into a little globule? What does it do? And different molecules for different purposes do different things, like actin, filament. Actin is the molecule in our muscles. That's a protein. And it's got this triple helix thing, and it's a long, thin thing that just kind of stretches out just like you kind of expect in a muscle. Whereas other molecules, like hemoglobin, for example, is another protein. Hemoglobin globules itself up into a little glob, and it has a little pocket inside it. And that pocket is where the iron atom goes in. That is the thing that gets used to transport oxygen in our blood. And so that's a different shape of molecule. And so the protein folding problem is the question, given if I tell you the sequence of amino acids that are in a protein, can you work out what shape the protein will be? And it's been a difficult problem because roughly what happens is some amino acids are typically amino acids they're sitting in water, for example. Some proteins are sitting in water. Some amino acids are hydrophobic in the sense that they're afraid of water. They like to sort of withdraw from the water that's around the molecule. Some are hydrophilic. They like to expose themselves to the water. and there are different forces of attraction between different amino acids and so on. And so you put all those things together, and then the question is, well, what shape will the protein be? And in a first approximation, you can say, well, there's the lowest energy, the thing that is the thing it most wants to be that shape. You can sort of compute with a computer what that will be, but it's very hard computation. And because there are many, many, many possibilities, and there's not an easy way to say, oh, it's going to be this way versus that way. And there have been basically two approaches to doing this. One is just from scratch, say, I know the force laws between all these different pieces of the protein. Now, what will be the minimum energy configuration? How will it fold up? That's sort of way number one. That's the first principles way. The other way is, let's just look at the 30,000 proteins or whatever it is now that exist that we know in humans, or 100,000, or maybe several 100,000, that whose structure is known, and let's just compare those with whatever protein we're being told. So, I give you a new protein. It's like, well, that's kind of like hemoglobin for a chicken or something. So it's, so therefore it will be this shape. So those have been two approaches. With modern machine learning, it does seem that it goes, one of these approaches wins, then the other one wins. I think these days it looks like with sort of modern machine learning that the approach of let's look at what's happened before and extrapolate from that seems to be probably the winning approach these days. But the question is, but it's also a very complicated thing, because it's not really right to say just in the abstract, how will the protein fold up? Because the protein gets produced somehow. When a protein is made, it's coming off a ribosome, it's being written sort of one amino acid at a time. And that process, if there are other molecules hanging around that are kind of chaperoning this process, they can affect what shape the protein will form into when it's originally created. And there are other things that can happen to the protein that will cause it to form into a different shape that are not just, oh, what's the minimum energy configuration? So it's a kind of complicated thing. And sometimes misfolding of proteins may possibly have important medical consequences in different cases. I mean, there are theories about Alzheimer's disease and so on that have to do with that. And there are prions and things which affect protein folding and all kinds of things like that. But so the question is, how can we make progress with this? And does our physics project contribute? I don't really see a connection right now between sort of what we're thinking about in our physics project and this problem of protein folding. It's my impression, though, the real challenge is, if I give you a random sequence of amino acids, what shape will it fold up into? Can you figure that out? Then you might say, well, okay, let's try it, let's test it. The problem is actually knowing what shape it made is actually pretty hard, because you've got this molecule, it's in some shape. How do you know what shape a molecule is? There are a couple of techniques, but the best one is probably X-ray crystallography. You have to make a crystal based on these molecules, and a big complicated molecule, it's hard to make it turn into a crystal. It's hard to line up all those molecules to get them to arrange themselves nicely to make a crystal. Once you have a crystal, you can use X-ray diffraction as a way to know what the shape of the things inside the crystal is, at least up to some ambiguity. But that's, I can talk about, if people are interested, maybe sometime I can explain how X-ray crystallography works. But that's kind of but you have to make a crystal of something, which is really quite hard if it's a big molecule. Okay. Let's see. So many interesting questions here. I'm just trying to a lot of interesting things here. Okay, let's try a few different things here. All right, we have a question from Emmett. How does black hole merging work? Okay. So, first of all, what is a black hole? A black hole is, the black holes that we mostly know about today are collapsed stars a bit more massive than the sun. They eventually use up all of their essentially nuclear fuel, and they they then collapse. And what happens is so much mass exists in the star and collapses that eventually the escape velocity becomes larger than the speed of light. For Earth, the escape velocity, if you fire a rocket out into space, if it's going more than 25,000 miles an hour, it will escape the Earth's gravity. For the sun, for example, if it's going more than 100,000 miles an hour, it will escape the gravity of the sun. When you have a lot of mass in a very small region, the escape velocity goes up. And there comes a point where the escape velocity is more than the speed of light. And at that point, nothing can escape the object. And that's why it's called a black hole, because things fall into it, are pulled in by gravity, but nothing escapes. At least that's roughly true. So what happens in a black hole merger is this. So, okay, so the sun, we're kind of the sun is an individual star with planets going around it. Many stars in our galaxies are binary stars. There are two stars that are orbiting around each other, and sometimes there may be planets orbiting around that binary star system. Sometimes you can imagine a very exotic world where you maybe even have a ternary star system and where you have planets that are having figure-8 orbits between, even with a binary star system, a sort of figure-8 orbit between the two stars. And you can imagine all kinds of weird things where you have different configurations of stars in the sky. It's a little bit of a downer for those kinds of things, that it's hard to maintain a stable orbit for billions of years that has sort of a figure-8 shape and so on. It might be possible, but it's a lot easier to maintain the kind of circular or elliptical orbits that we have around a single star, or to maintain orbits outside of the binary stars are orbiting around very close in, and then there are planets much further away. But in any case, so a lot of stars in our galaxy are binary stars. So one thing that can happen is you can have two binary stars, and they both reach the sort of end of their life as stars, and they both collapse at different times probably and turn into black holes. And so you have these two black holes orbiting each other, a binary black hole system. Okay, so then what happens? Well, normally when if things are orbiting each other, for example, with the moon orbiting the Earth, the moon slowly moves slightly further away from the Earth as a result of the moon is just gradually losing angular momentum and moving slightly further away from the Earth. What can happen in but there are other cases where things spiral in, and usually you have to lose angular momentum to spiral in. You have to either be something has to be sort of some kind of frictional force of some kind has to be making you kind of lose that angular momentum, so that you're no longer just in orbit going around. It's like when you twirl something around, if there wasn't any air resistance, it would just keep twirling forever. But the question is there resistance that causes the thing to slow down? As it slows down, if it's the sort of centrifugal force that's holding it out in the orbit, and if it slows down, then it gradually will sort of spiral in, and then the things will crash into each other. So what happens in a binary black hole system is that gradually the black holes lose energy, lose angular momentum, they spiral in to the point where they crash into each other. So why do they spiral in? There are a variety of different effects. Some effects have to do with accretion disks and gas and so on, but other effects have to do with the emission of gravitational radiation. Let's explain how that works. So normally, if we have an electric charge, for example, and we just wiggle the electric charge up and down, that will make an electromagnetic wave, a radio wave. That's it's the way that works. Is just the motion of a charge produces, actually the acceleration of a charge produces an electromagnetic wave. It has an electrical effect and also a magnetic effect, and it produces this electromagnetic wave. So a prediction of Einstein's general theory of relativity from 1915 was that there should also be gravitational waves, that it should be possible, if you have a massive object that produces gravity, that it should be possible by kind of squidging the object around to have it produce gravitational waves. Just like a moving charge produces electromagnetic waves, so in a sense, a moving mass produces gravitational waves. It's a little more tricky. If you just move a mass up, down, up, down, up, down, you won't get gravitational waves. You need to basically have a mass that kind of goes, it's a quadrupole deformation where the mass kind of squashes down and comes out and like that. But when you have one mass in orbit around another, you do get gravitational radiation. That, in fact, I think Einstein even worked out the formula for that, the rate of energy loss due to gravitational radiation. But in any case, what happens is what gravitational radiation produces this, so gravity is interpreted as this kind of deformation of space, and gravitational radiation is this sort of wave-like deformation of space that moves, so far as we can tell, at the speed of light. And one consequence that wave-like deformation of space has is that if you have the appropriately arranged collection of masses, that deformation of space will move those masses slightly. And what happens in a black hole merger is that these black holes, these pair of black holes, they're losing energy, perhaps through gravitational radiation. They eventually lose enough energy that splat, they ran into each other. And in a few seconds, what has to happen is that these two black holes, which were these nice, basically spherical things, or more or less spherical things, they merge with each other. And that process is a very violent process. And in fact, in that process, some part of the mass of those black holes is converted into pure energy in the form of gravitational waves. And some part of it ends up making a bigger black hole. So in the first black hole merger that was detected a few years ago by a gravitational wave detector, that was, I think it dissipated about 1.5 solar masses in a matter of a couple of seconds. So that means that what was happening as these two black holes merged to turn into one black hole, it was such a violent event that the equivalent of 1.5 times the mass of our sun was converted into pure energy and gravitational waves. And that meant that even though that event was happening 1/3 of the way across the universe, we could still detect it with a gravitational wave detector here on Earth that was measuring deformations in distance, moving of masses by amounts that are a small fraction of the size of an atom. So it's a subtle effect, but still that merger of black hole, 1/3 of the way across the universe, still had a measurable effect here on Earth. So one question is, well, these two things run into each other and they make another black hole. What are they really making? How does that really work? Well, one feature of black holes, it's called the no-hair theorem for black holes. It basically says any black hole is like any other black hole. All you need to know about it is its mass and how fast it's spinning around. And that if you have a black hole that isn't spinning around at all, it will always be a perfect sphere. Its boundary, its event horizon will always be a perfect sphere. And there's nothing, when you look at it from the outside, there's nothing, it just looks like a perfect sphere. And that's a prediction of general relativity that should be that way, that there are no bumps on it. It's not like it's the surface of the sun where there are all kinds of, solar prominences that are coming out and all kinds of things like that. No, it's just as far as the gravitational part of the black hole is concerned, it's just a perfect spherical thing. Now, what happens inside the black hole? Well, we won't get to know that because, at least for the most part, because anything that falls into a black hole doesn't get out again. And so it's like something could be going on. There could be this whole elaborate thing happening inside the black hole, but it can't signal to us outside. So it's as if we don't, as if it doesn't matter what's going on. It's actually a very subtle thing. What happens inside a black hole is not really that well understood. It's known that outside it will kind of look like this perfect sphere of event horizon, but inside, who knows what's happening? And maybe there's even a place where the usual structure of space-time breaks down. That's both what general relativity says and it's what our models say. Actually, more to the point, in a non-rotating black hole, there's a very bizarre thing at the center of the black hole. There's this place where time simply stops, where the progression of time just comes to an end. Boom, it's stopped right there. So all kinds of weird things happen. But from outside the black hole, all you know is this perfect sphere. Well, if you have two of these perfect sphere black holes and they merge with each other, somehow the end result has to be a perfect sphere. And in the process of it turning into that, they kind of blobs around. It's kind of like a bell where you ring the bell by, it's a big sort of thing, and it gradually kind of, what will happen is it gradually deforms, and eventually, after a sufficiently long time, it's kind of lost enough energy through gravitational radiation, it ends up in this perfect sphere form. And we get to see the little wiggles as that ring down process happens. And for the case of the first black hole merger, I think it was about 5 seconds of, and after 5 seconds, it's all over. All of those fluctuations from the very violent event of the formation of that merged black hole have gone away. Now, today, I think the gravitational wave detectors are seeing maybe an event every day or so. So it's somewhere in the universe, there's a black hole merger every day or so. And that's, we can kind of work out how that works. There are about 10 to the 11 stars in our galaxy, 100 billion stars in our galaxy. There are about 100 billion galaxies. That tells us how many stars there are in the universe. We know how many binary stars there are. We know, et cetera, et cetera, et cetera. We can work out, and I think probably we're at the point where we can see most black hole mergers that happen anywhere in the universe. And that's it's kind of a remarkable thing that one can kind of tell that. It's a little bit like, if there's an earthquake that happens anywhere on the Earth, seismometers can detect it. It's sort of the same kind of thing, but for the structure of space, observing black hole mergers anywhere in the universe. Okay. Question here from Jonas about, is there a theory about what type of particles a black hole will be made of? Yeah, well, that's a subtle thing, because the very idea of a particle, we got all these particles, electrons, protons, whatever. When a black hole is formed, all of those things collapse and they're all being pulled by gravity. And the effect of a black hole is this deformation of space that results in this event horizon where things can go in but can't come out. And so all of the things that were all the features of particles, they're all irrelevant, because all we see in a black hole is something to do with the structure of space. And in that sense, a black hole is not made of particles. A black hole inside the event horizon, all bets are off about what's going on. It's a more complicated story. But as far as the structure of this event horizon, it's a feature of space. It's a feature of the structure of space. It's not something that is made of material particles. Now, if we really want to get funky, there's the following question. We talk about big black holes made from collapsed stars and things like that, but what about really, really tiny black holes? One thing that I've thought was a possibility, actually, since I was a kid, and I didn't really, the ways in which it might be a possibility have changed a bit. But one of the really bizarre possibilities is maybe all the particles we know and love, like electrons and quarks and so on, maybe they are in fact really tiny black holes in some sense. And I think there's a pretty good chance that that's true. And that, in fact, in some sense, and it's a little bit of a subtle sense, all those things are like absolutely tiny versions of black holes that are like little regions of the universe that work in a different way than other regions of the universe. But in an ordinary black hole situation, what you're seeing that counts as the black hole is a feature of the structure of gravity and the structure of space-time, not something directly made from material particles. Let's see. Okay. Gosh, there's a question from Yosef. This is one I'm not, an unexpected question from, what's my experience and opinion about alchemy? And is it possible to incorporate a modernized version of it into Mathematica? That's a weird and funky question. Thank you. Okay, well, first of all, let's talk about what alchemy is or was. So back in, particularly in the Middle Ages, people were trying to understand what these days we would think of as chemistry, how different materials can have chemical reactions, produce other materials, and so on. At the time, there was a lot done on metallurgy, on how you can go from the ore of a metal, iron ore, which is just kind of a rock, and how you can get out of it something which is just metallic iron, or how you can do that for aluminum, which is more difficult, or maybe my favorite element, tungsten, whose principal ore is wolframite, WO4. I actually don't know as much as I should about how you get tungsten out of wolframite. That's kind of embarrassing. You heat it up, you combine it with some other chemical, and you get tungsten out, but I'm not exactly sure how it works. But anyway, so there was a lot done of trying to figure out how you could go from like a rock to metal, how you could heat it up, have it react with other things. And what's happening in those chemical reactions, as we now know today, is that individual molecules associated with the rock are being broken down, and the atoms that are in them, that are these atoms of the metal, are coming out, and they're forming into this whole substance, which is the metal, and so on. Okay, so a lot of the sort of question of alchemy was there some way? The particular one that people were most interested in was the transmutation of lead into gold. Lead is a pretty cheap material that's pretty common. Gold is pretty rare, and has been considered pretty valuable. And the question is, could you somehow in your lab just go and take a big lump of lead and turn it into gold? And if you could do that, then it's kind of like people often claim for people do in the in financial markets and things. You make money out of nothing, so to speak. Actually, it's usually lots of hard work to do it, but quite different topic. But in any case, so the question was, could you do things like transmute lead into gold? And so people had a whole elaborate ways of trying to do that, and all sorts of skullduggery of figuring out magical ideas for how that might work. In the end, it didn't work. Finally, it was understood that lead and gold are really different kinds of atoms, that the nucleus of the lead atom is different, has a different number of protons in it than the nucleus of the gold atom. And by purely chemical processes, by purely sort of heating things up and to ordinary temperatures of a few thousand degrees, maybe in a flame, you can't make lead and gold transmute into each other. Now, what was discovered once nuclear physics was understood in the 1940s and 1950s is, well, yes, if you have high enough energy particles and you can really monkey around with the nuclei of these elements, yes, you can do things like you can take a lead nucleus and you can knock out some of its protons. You can knock it down so that it's a gold nucleus. But that process is hardly a cost-effective process for making gold out of lead. But so the sort of the idea of alchemy was this: what were the mechanisms by which you can transmute one material into another? And that really turned into what became modern chemistry. I mean, modern chemistry was really, once people started understanding that there were atoms, which was kind of early to mid 1800s, and then by the late 1800s, there was sort of the huge development of industrial chemistry, and the concept that you could really make things. And then later in, when was it, 1910s, 1920s, plastics, for example, which are long hydrocarbon molecules, it was understood how to create those. And those were the first kind of really successful synthetic materials which hadn't existed in nature, but which were created by chemical reactions and so on. And that was kind of what the whole business of alchemy turned into, was chemistry. Chemistry is in chemistry, what you expect is that you're going to make something in a chemical reaction, and it's like heat this, pour in this, cool this, do that, do the other thing. And typically in industrial processes for making things, the most sophisticated these days will have maybe 20, maybe 25 steps in them. Do this, do that, do the other thing, put it in this machine, use this catalyst, do this thing, et cetera, et cetera, et cetera. It's sort of an interesting question of, could one extend that? If you said, let's make something where we can have 100 steps, where we make a material by using 100 different steps, then what kinds of things could we do? And there's some hope that with kind of automated labs and more kinds of sophistication in terms of the way one computationally thinks about designing chemical synthesis processes, the process of going, if you're trying to make some chemical, what you end up having to do, you've got these molecules, you're trying to rearrange the molecules. So one little ring from one molecule turns into something which attaches to something else. It's very hard to do that. You can't say, let me just pick up the atoms and do this to them. What you have to do is do it very indirectly by knowing, oh, when this molecule is in this state, it will have some electric charge that will pull on this, that will align with this molecule and pull in this way and do things kind of at the level of molecules. That's a hard thing to figure out. And this process, actually, there's some ideas recently that we've had on sort of how to automate the process of doing chemical synthesis, of trying to figure out just what series of moves do you have to make to turn a chemical, a molecule, to go from having a trillion molecules of this type to a trillion molecules of that type. Just what sequence of moves do you have to go to get from here to there, and how do you get it to the point where enough molecules have gone through whatever process you're defining that you get a significant amount of the material you're trying to produce. So that's sort of the modern version of that. And the question of actually, we've done a lot of work in Wolfram language in recent times to support molecular computation about molecules. Just as we can compute things about, I don't know, images or graphs or mathematical formulas, so now we can compute things about molecules. And that's sort of a precursor to being able to do these kinds of things that I'm talking about, like more streamlined automated chemical synthesis and so on, in a sense, doing with what we know about chemistry, doing in a sense what the alchemists wanted to do, coming up with a procedure for going from here to there, for being able, and really the ultimate goal is, I draw you a picture of a molecule, you make that molecule. That's not something that one can do in chemistry today. It's a very difficult thing. There are particular molecules and particular complicated synthesis processes get invented to do them. I mean, back in the day, people would say, I draw you a molecule out of carbon atoms that looks like a dog. Can you make dogacine? Can you find a series of chemical reactions that will make a molecule that is in that shape? Well, it would be nice to have a sort of systematic way to do that. Perhaps, we don't know for sure, perhaps by having appropriate shapes of molecules, we could achieve all kinds of things. One of the things that's difficult to know is, given a particular molecule, a particular shape, what are its properties going to be? That's not an easy thing to work out either. I mean, one of the things that was a big surprise for carbon, okay, so carbon exists in two common forms. It exists as graphite and it exists as diamond. So in graphite, the atoms of carbon in graphite, it's crystal, but the atoms are arranged in these sheets. There's sort of sheets of carbon atoms that make up a piece of graphite. And so it has various properties, like it can slide and so on. Diamond, exact same material, just a bunch of carbon atoms, but diamond, the carbon atoms are arranged, but when diamond is produced, for example, at high pressure, the carbon atoms kind of move around so that they're packed in a certain way. In a diamond crystal, they're all arranged in this particular geometrical structure, all infinite. It's sort of a very large thing, which is just repeats. The same structure repeats. So that's the two forms of carbon that were known for a long time were graphite and diamond. But it turned out there was actually another form of carbon that people hadn't discovered, called, it's often called Buckminster fullerene, after Buckminster Fuller, and what it is it's carbon atoms that are arranged not in an infinite crystal, but they're arranged in a little cluster that basically is like, if you have a soccer ball, which has pentagons and hexagons, you don't look at the pentagons and hexagons, you look at the corners between all of those. And you look at the network of corners, and you just then, it turns out that this version of carbon is made from carbon atoms that are arranged at the positions of that network of corners that you would find on a soccer ball. And so that's a carbon 60 is the 60 of those points, and that's at least the simplest form. And that's a different form of carbon. And there's also a version of it where you can make it into tubes, so-called graphene tubes, where you've essentially got, it's a slightly different thing. It's kind of like miniature version of graphite all rolled in a tube. And that probably has some very interesting properties. It's a very good electrical conductor. It has all kinds of other interesting properties, and it may be the future even of what certain kinds of electric circuits are made out of. But in any case, that form of carbon, the buckyball form of carbon, wasn't known until the 1970s, even 1980s. And it's actually very common. It actually exists in soot and things. It just, there wasn't a good method for even detecting that it was there. And then once you have it, it's like, what's it good for? You know, I think as such, the buckyballs as such, I don't think have found that many uses. I mean, there was a kind of a whole non-stick frying pan story with that, but I'm not sure if even that panned out, not to make too much of a pun. But in any case, but the basic point is, you know, let's say sort of a holy grail of kind of meta chemistry is just make a molecule in whatever shape you want. But one of the challenges is, what shape do you want? What shape of molecule will be useful? Some molecules, for example, might have little pockets in them that could have, I mentioned hemoglobin, where you know, there's a little pocket that fits a single iron atom into it. And that's useful. You could imagine a molecule which would have a little space inside it where, for example, it would have something where it would have some effect where, you know, with electromagnetic radiation, for example, you get the molecule to do something very special with radiation of a certain frequency because it has a little pocket which has some particular thing inside it. Maybe that will be useful for delivering drugs internally for something, or something like this. But you know, it's kind of a, what's your imagination about what the molecule might do, and then how do you actually make it? And is there a systematic way of kind of creating the kind of the chemical, doing a series of chemical actions to produce a molecule of exactly that form? Okay, I think we should wrap up fairly soon here. Let's try and do a few more of these. Okay, there's a question. It's a question from Ringmaster about the nature of time travel, time machines depicted in science fiction stories, and so on. You know, time travel is a bit of a logical mess. In our theory of physics, time travel is simply outright definitionally impossible. Okay, so let's talk about time travel. The most interesting time travel is time travel to the past. Time travel to the future is a little bit of a weird business, because one-way time travel to the future is pretty easy. You just do nothing. You just sort of hibernate. You say, like, if you're a computer and if your brain was sort of a computer's, and you say you want to do time travel to the future, okay, just stop, just switch yourself off for 10 years and then wake up again. Okay, you've time traveled to the future. That's one version of it. What does it mean to time travel to the past? It means that you're somehow, from what you know now, you're going back to affect something that happened in the past. How does that work? Well, in our view of time, in our model of physics, for example, time is the inexorable process of the universe computing what it will do next. And that's not something where you can say, the universe has computed what it will do next. Okay, it's going to go back and compute something it already computed. That just doesn't make any sense. Now, in the mathematical theory of general relativity, of the theory of gravity, it is possible to have what are called closed time-like curves. A time-like curve is a curve where what to some entity that's following this sort of path through space-time, it's as if time is progressing as you go down along this curve. And a closed time-like curve means it just seems like time is progressing to the future. As far as you're concerned, time is progressing to the future. But when people look at you from the outside, it's as if you went back in time and you make a closed cycle where you're progressing to the future, but actually you go back in time and then progress to the future again. Well, the presence of those things, even in the mathematical theory of general relativity, is actually a very strange and problematic thing. But really what that means is, when there is a closed time-like curve, what it really means is that there has to be a certain consistency between the past and the future, because the past and the future are more connected. Usually the future is connected to the past only by virtue of the fact that the future emerges by doing things, by computing things from the past. But when you have a closed time-like curve, it is as if the future is connected to the past in a more detailed way. And so that means there has to be sort of consistency between the future and the past. And so in your average piece of science fiction, it's it's kind of like you're thinking what's going on, and you're going to go and the future for you is going to the past. And that just doesn't make any sense, because the way that that has to work is if your future becomes past, then there has to be consistency between what happens from that past and what happens in your actual future. And so really these closed time-like curves just add a certain consistency condition about how the past and the future have to be consistent. And that doesn't mean that you get, as a matter of sort of thinking about what's going on, to think, oh, I could, the real issue is, could you choose to do anything different in the past? The answer is no, because really the existence of this closed time-like curve has already defined a consistency between the past and the future. So the notion of time travel, where you say, I'm going to decide to go to the past and decide what I'm going to do in the past, it just can't work. It's just not a sort of logically consistent thing to imagine. So despite the fact there's all kinds of nice fiction that you can make based on it, but I don't think it's something you can really produce in reality. All right, 2 last questions here, and then I need to wrap up. Question from Jonas here. About whether there can be things like computer architectures that don't use binary arithmetic circuits. Will they be used in the future? So one feature of computers as they exist today, so at the lowest level in a computer, what you're dealing with is bits. Are there electrons there, or are there not electrons there? 1 or 0. And there's a sort of question of, can you make other kinds of systems that don't just deal with a 1 or 0, 1 or 0, whole giant arrays of billions of ones and zeros? Are there other things you can do? So one thing people imagined in the early days of computers is maybe you do better if you had 0, 1, and -1, or 0, 1, and 2, like ternary computers, where you have not just 2 possible states, but 3. Doesn't really make much difference, because if you can encode 3 different states, you can always do that with a pair of binary bits. You just say 0, 0 represents 0, 1, 1 represents 1, and let's say, I don't know, 0, 1 represents 2, or something like this, however you choose to do it. More consistently, you say 0, 0 represents 0, 0, 1 represents 1, 1, 0 represents 2, 1, 1 represents 3. You're just using pairs of bits to encode those different things. But people did in the early days, in the 1950s, actually, people built like ternary computers. There was a famous Russian computer that was a base 3 computer. I don't think it had any particularly notable features. Certainly the way that you do arithmetic, there's some little elaborate tricks to do with the way that you deal with negative numbers and things that can be done in ternary arithmetic, but it's not notably different. The one thing that one could imagine that would be notably different is to not use a digital computer, but instead to use more of an analog computer. So the reason our current computers are called digital, it's like, counting in your fingers. It's like 1 finger, 2 finger, 3 fingers, 4 fingers. It's not like we say we have 1.726 fingers. It's like it's whole numbers of fingers that we're dealing with. And that's kind of the notion of digital computers, is that everything is just whole numbers, ultimately made from ones and zeros. But analog computers, the idea is that there is a continuous kind of sliding scale. Instead of saying there's a 1 or a 0, it's like there's any number between 0 and 1. Analog computers were also popular in the 1940s and 1950s. They didn't really work out very well. What happened is, in an analog computer, it's like a typical electric circuit where you can say, well, I've got this voltage, I've got 6 volts, I've got 6.027 volts, I've got 6.1 volts. There's a kind of a arbitrary voltage that you get somewhere. And that's and so you can imagine just arranging the voltage to mean whatever you want it to mean. There were a number of reasons why it didn't work out that well. One reason was it was hard to know exactly what you were computing. If you're doing that kind of computation and it's off by a little bit, well, the number's just off by a little bit. But how much of a little bit is enough that you get nonsense? When you're dealing with digital computation, it's like the bit is either correct, it's a 1, or it's incorrect, it's a 0, let's say. And it's easier to correct for errors in that type of situation. You can do extra computation. You can check consistency of things. You can say this is right, this is wrong. An analog computer was much harder to do that. It was like, well, it's a bit wrong, but we don't know whether it's so wrong as to be misleading or not so wrong or whatever else. Also, as we move towards our current theory of physics, ultimately analog computation will not get you anywhere. The universe is ultimately really made of digital things. It's ultimately made of discrete points and so on. So ultimately, at a sufficiently small scale, although it's a scale unbelievably much smaller than what's relevant for practical technology today, on a sufficiently small scale, analog can't win. But on the scale of actual existing computers, it might be useful. And it must be said that in a typical computer, there is analog electric circuitry. For example, there's less and less of it actually, but sometimes things to do with power supplies, sometimes things to do with maybe sound generation, sometimes some other things like that. They're dealing with these sort of continuous scale of voltages rather than just on or off type things. There also are there have been repeated efforts to do things like image processing using analog circuits, maybe to do things with neural networks, where you're having artificial neural nets, where instead of just saying it's on or off, you say, well, it's a sliding scale. Maybe that's even more realistic to how biology does it, although I don't think so. I mean, biology, actually, strangely enough, you might have thought biology would just be, oh, there's a certain concentration or not. But actually, there is little vesicles of neurotransmitter that seem to exist, where it's like you only get, you get 100 vesicles or you get 105 vesicles, and you don't have a kind of a continuous sliding scale there. But so it's not looking so promising that there can be something different from there may be some small optimizations that can be done, but the whole, another issue is the whole apparatus of kind of inventing software and so on. That's all deeply based on the idea of digital computers. We know how to program digital computers. We know this idea of universal computation that works for digital computers. We don't have any similar idea for analog computers. It's an interesting question. In a digital computer, you can have a fixed piece of computer hardware, and by feeding in a different program, you get the computer to do different things. There's a question, if you were doing that with an analog computer, is there a way of making a universal analog computer whereby just setting a bunch of switches and things differently, you get it to do any function, any analog function? Nobody knows. Actually, there's some interesting mathematics around that question, but it's a pretty undefined, it's not well understood. And it's something where it's like, well, making any function you want, you can say a mathematical function, you can plot it, it kind of wiggles up and down or whatever, or it makes it's some smooth curve. You say, well, I want any curve, however wiggly it is. And that gets to be a very difficult mathematical question to define what you mean by that kind of wiggliness, what kind of wiggliness you can put into the program that sets up the wiggly out curve that you're trying to produce and so on. It's all a bit complicated and it's not well developed. And my feeling is that probably I don't think it's going to be that fruitful. All right. One last question here from Vienna. I'm currently in high school. What advice would you give to an aspiring mathematician? Mathematics is, by aspiring mathematician, I am assuming that you mean research mathematics. So discovering new things in mathematics. One feature of mathematics is it's an old field. It's been, the set of things we know now are built on a tower that's been being constructed for hundreds of years. And so a lot of the frontiers of mathematics as they exist today, you need to climb that whole tower. You need to learn the whole series of levels of different kinds of things that exist in mathematics. Now, what happens is every so often, people will invent some new level of abstraction where you say, oh, you don't need to learn determinant theory. You don't need to learn the theory of invariance. Determinant theory, you just learn linear algebra because linear algebra sort of covers all of the detailed things that were worked out in determinant theory. You don't need to learn invariant theory because that's all covered by the theory of group representations, that's sort of a more general theory. So that kind of thing can happen, but it's still a complicated tower of things that you have to learn. I think what happens in every field is when new methodology comes in, you start to be able to do new things that often that allow you sometimes to make progress without having climbed the whole tower that exists. And the big thing in mathematics is experimental mathematics and the use of computation to find out what's true in mathematics. See, most of mathematics, as you would learn it from kind of the way that it's presented in academic journals and things, it looks like people do mathematics by saying, oh, there's the theorem we figured out is true, let's now give a proof of that theorem. Truth is, many of the great mathematicians, Euler, Gauss, many other people, even Riemann, people like that, they did experiments. You know, Gauss figured out the prime number theorem by actually making a table of primes and seeing that the density of primes had some particular form, and then saying, let me go try and do a bunch of math to understand why it works that way. This idea of experimental math, where you imagine some question and you just do what today will be, in Gauss's day, it was, you know, doing it by hand, but today will be use Mathematica, use Wolfram language, whatever, to do, you know, to just do the computation to find out what's true. That's a hugely powerful thing. And it's something where it's been, you know, only the tiniest corner of that has been explored. And what's really exciting about that is you don't have to climb the whole tower all the way up to sort of graduate school mathematics to be able to make contributions when you ask the right questions doing experimental mathematics. Asking the right questions isn't always easy. That requires a sort of good conceptual understanding of where sort of mathematics is going, what the structure of the field is, and so on, to be able to ask questions where they're going to be interesting, where the answers are going to be interesting. Sort of a famous example of this, Ramanujan, Indian mathematician around 1910-ish time frame. You know, he was a very good hand calculator, and he came up with all these incredible formulae. You know, e to the pi square root of 163, I think that's right, is almost exactly an integer. He discovered that. You know, all kinds of weird formulae like that, discovered by doing essentially his version of experimental mathematics. But he had very good intuition about what was worth looking at, and that, like, e to the pi square root of 163, I think that's right, he's like, rather than just like, oh, that's a coincidence, he's like, well, actually, that tells you something very deep about lots of things. And in fact, that particular formula turns out to be one of the main methods for computing the digits of pi now. And it's deeply related to the theory of elliptic functions and all kinds of other things. Ramanujan didn't work out all those connections, but he had a very good intuition for what were experiments that were worth doing, in effect. And in fact, in his case, it took decades longer before people started filling in and understanding how what he'd done actually related to other areas of mathematics. But if you start from sort of existing areas of mathematics, you say, what can we now do by doing computer experiments? What can we now discover that's something that is accessible at sort of a high school level, actually? And the thing to understand is, you know, in doing research, there's sort of two pieces. There's what question you're going to ask and how do you answer that question. And people, a lot of the educational process is about, given a question, how are you going to answer it? What the education process usually doesn't have in it is, well, what question should you ask? But in terms of success in research in mathematics or other fields, it's actually the much more important effect is, what question should you ask? And so kind of practicing the process of ask a question, wonder about something, go look at the distribution of you know, ternary primes or something, go see whether you can figure out why it works that way, do the experiment, see what's true. I think that's a really good driver, a modern driver that isn't what you would find and it's not what your average kind of math professor is going to tell you to do, because that's just not been the practice of mathematics as it's been done over the past, particularly over the past probably 50 years or so. But I think that that's a fantastic opportunity, and I've seen in the course of the last 30-something years, since Mathematica first existed, a bunch of people make wonderful careers that have sort of been launched by just doing experimental mathematics in a bunch of different directions and finding out a lot of things that are true. Now, you know, one of the interesting meta points is, if you just do an arbitrary computational experiment and you get an answer, sometimes those computational experiments maybe, and you make some hypothesis that seems to be true based on what you did there. the question is that hypothesis something that is at all reachable by existing mathematics, or is it undecidable for existing mathematics? Is the length of proof you need to give essentially infinite? What happens if you just sort of drop in arbitrarily asking a computational question? You can end up with these questions that are sort of infinitely far away from existing mathematics. But if you inform your questions by things that are already known in mathematics, that's a good place to start. And I think, the thing that is really interesting to do at kind of a high school level today is, go use Mathematica basically, and go figure out a bunch of, just wonder about math, try some things out, see what you think is true, see whether you can prove that that's true. Maybe the proof is just I run it and it does it. But it's amazing when you start to really open up and just think about, well, what kind of mathematics question can you ask? It's amazing how much you can find that their questions just haven't been asked. I mean, I was looking at one recently. It's one that was kind of a small thing in my book, New Kind of Science. I was looking at, instead of Fibonacci series, so the Fibonacci series says f of n is equal to f of n minus 1 plus f of n minus 2. And, you started off with f of 1 is 1, f of 2 is 1. And then it goes 1, 1, 2, 3, 5, 8, et cetera, et cetera, et cetera. There's a more complicated version of that in which you have a sort of nested Fibonacci sequence where you say f of n is f of n minus f of n minus 1. Instead of f of n minus 1, it's the f of, and the argument of the f is n minus f of n minus 1. Those kinds of things. If you can rather easily from that make these series which bounce around all over the place, and nobody knows anything about them. And it's kind of amazing. And yet there's one actually that we found at our summer school when we first did it in 2003, that particular series, a bit like that, generates prime numbers. And it's like, how could this be? There's not supposed to be a formula for primes. And actually a person who was at that summer school, who's now a math professor, did a whole analysis of this and figured out how it all works and wrote a paper about it and so on. But that was something that came out of just sort of doing the experiment, and then it turns out to be an interesting piece of mathematics. So that's a few comments about the aspiring mathematician thing. Is there's a place, experimental mathematics, where you can immediately jump into doing mathematics research and get sort of a feeling for that process of inventing questions and answering them and so on. All right, I think that's, we ran out of time very much for today. Thank you all for all those great questions, and look forward to seeing you again next week. Bye for now.